Okay, good afternoon. We'll be starting on a new topic today, which is known as magnetic circuits. What is a magnetic circuit? So we are going to basically now venture into studying about power apparatus like transformers, electrical machines, measuring instruments, and so on. So all of them actually encounter something called, in all of them you encounter something called magnetic circuits. Okay. So if you look at magnetic circuits, the magnetic circuit is essentially a closed path followed by magnetic field lines. That is the definition of a magnetic circuit. So magnetic circuit is a closed path followed by magnetic field lines or flux lines, you can say. Magnetic field lines or flux lines. Okay. So first of all, we have to understand what is magnetic field line or flux line and what do we mean by it follows a closed path. So just like how a current can flow, if I talk about a voltage source which is connected to a resistance, I'm going to say that the current can flow only if there is a closed path. If there is no closed path, there cannot be any current. The same way, if you look at a magnetic flux line or field line, it has to have a closed path. Without closed path, it will not be able to flow at all. So for example, if I am going to have, let us say, an iron ring like this. So I am talking about an iron ring, which can have probably a circular cross section or something. If I look at the cross section, it can be a circular cross section. So if I have an iron ring like this, and let's say around this, I'm going to wind a winding. So this is going to go like this, and I'm going to have something like this as the winding which is wound around. Okay, so it's like this, and I'm going to take the wire out like this. So let's say I am passing a current which is I here, and it is returning like this. Of course, it's a closed path. It has to go elsewhere and end. And let's say there are number of turns which is n. This is the number of turns which is going to be n. So this current which is flowing through this winding, which is wound around, let us say, an iron ring. I'm calling this as an iron ring. Okay. So this is going to set up a flux which is going to be like this. So the flux line, whatever goes through this iron ring, is going to have a closed path somewhat like this. Let me probably draw this in a little different color so that it is clearly visible. So I'm going to have a flux line which is going to go like this in the same circular path, and it is going to go around like this. So this is the magnetic flux line. This is going to be the magnetic flux line. So this magnetic flux line, what I have got, this is a closed path. So if I talk about magnetic circuit in this particular system where I'm going to pass a current I with n number of turns, which is wound around some iron ring like this. So this particular green color path, what I'm showing, I'm calling that as the magnetic circuit. So if I'm talking about what is the length of the magnetic circuit here, the length of the magnetic circuit is going to be essentially whatever is the length of this magnetic field line. So magnetic field line, you can say, when I talk about the inner circumference of this ring, so it will be 2 pi r, where r is the inner circumference, inner radius. And if I'm talking about the outermost line, then it will have the outer circumference or outer radius. So what we will do is we'll generally take the average. So I would take this as mean circumference of this ring. So that is going to be the length of the magnetic circuit. So whenever I'm going to have a magnetic circuit which is having maybe different kind of radii, then I will try to take the mean radius, and then I would say this is if radius of the outer side is R0 and radius of the inner circumference is Ri. So R0 plus Ri divided by 2, this is going to be R mean. So I would say 2 pi R mean happens to be the length of the magnetic circuit. This is going to be the length of the magnetic circuit in this particular case. Okay. Now, whenever a magnetism is established, a flux is established in a magnetic circuit, or a field line is really created because of the current flowing in a magnetic circuit, in that particular case, I call the number of turns, whatever is here, how many number of turns through which the current is flowing, multiplied by the current itself. This product is generally known as the magnetomotive force or MMF. We call this as MMF. So MMF or magnetomotive force is going to be the root cause which really sets the magnetic flux in action. Why the magnetic field is manifested? That is because of how many number of turns are carrying the current in this particular magnetic circuit and how much is the current that is flowing through this particular magnetic field. So the magnetic, the root cause for the magnetic circuit, the coil which is causing the magnetism to happen, how many amperes of current is flowing through that, and what is the number of turns that this particular coil is having. Both of them are going to play a very, very vital role in deciding what is the kind of magnetism that is established. So magnetomotive force is the root cause for all the magnetic circuit manifestation in this particular system. Just like how a voltage source causes current flow, right? The same way, the voltage source is sometimes indicated as EMF. The same way, we are going to say in a magnetic circuit, MMF causes flux being established, or the flow of magnetic field lines, the establishment of magnetic field lines. So that is going to be caused by MMF. So what we are going to study in this particular topic is whenever we are going to have a current flowing through a conductor which is probably wound in the form of a coil or a single conductor that is carrying current, how exactly magnetism is manifested around it, how do we do the calculations corresponding to magnetic flux and magnetic flux density. So that is what we are going to study in this particular topic in magnetic circuits. Okay. So if we are considering a coil which is probably carrying a current into the board, so I'm going to show it as a cross. Okay. So I'm sure all of you must have heard of the thumb rule. If I am holding my, let me probably show my video here. Okay, so if I am going to talk about all the currents that are shown by the edge of the finger, that is the dot, then I'm going to have the current is actually facing me, which is the dot, then the magnetic field line is going to be exactly indicated by the direction of the thumb. Okay, so this is generally the thumb rule for the magnetic circuit. So if I'm going to have the currents in a particular direction, I'm going to have basically if the dot is indicating the current that is coming out, then in that case, the thumb is going to show the direction of the magnetic field. So by writing that, I should be able to say, okay, so if I am having a cross current, right, if I am going to have a cross current, so I should be able to write what is the direction of the magnetic field line. So I'm going to have a magnetic field line which is surrounding this. This is the way it is going to be, whether it is clockwise or anti-clockwise. That is what I need to look at. So I can tell, in fact, just like how the thumb is indicating the direction of the current, the same way I can say, if, let me again show my video. I hope you are able to see my video along with this. So if I see the dot, right? So if this thumb is indicating the direction of current which is coming out, the curvature of my hand, in what way it is curving, that is showing the field line. So either way, that is by looking at dot, I can say what is the direction of the magnetic field. The same way I should be able to take my thumb as the direction of current. So if I take this thumb as dot of the current which is coming out and hitting me, and this curvature of my fingers, that show essentially what is the direction of the magnetic field lines. So I should be able to say, if it had been a dot current, then I should have had the field lines in this direction. But because this is a cross current, I'm going to have the field line in clockwise direction. So I'm going to have the field line. If I try to draw the magnetic flux line or magnetic field line, it is going to be in the clockwise direction. So this is the direction of my magnetic field line normally that I'm going to see. So there will be several concentric lines. So I should have inner line like this, one more inner line like this, and so on. So I will have many lines, magnetic field lines going around through this particular, concentrically around this particular conductor. Okay. So whenever I talk about only one conductor that is carrying current, if I talk about the magnetic field line, it is going to be in a particular direction. All of them are going to be in a particular direction. Okay. If I have the return path for this conductor, so this conductor is carrying current inward. So if I talk about this conductor as though it is carrying current inward, there should be definitely another conductor which is carrying current outward this way. So that will also have definitely the magnetic field lines around it like this, but it will be in the opposite sense. So if you want to cancel out the magnetism, only way you can very easily do it is to have another conductor which is carrying current in the opposite direction. That will automatically cancel out the magnetism. Okay. But if I assume that only one conductor is basically carrying current, and if I want to see what is the kind of flux that I'm going to have at 1 meter distance from here. Okay, so the flux is always measured, magnetic flux is always measured in Webers. And if I talk about what is the flux per unit area, that is actually the flux density. I call that as flux density. So flux density is going to be Weber per meter square, which is also generally indicated by Tesla. So Tesla and Weber per meter square both are units for flux density. And similarly, we say MMF, which is going to be number of turns multiplied by ampere or the current. So I should say this as ampere turn as the unit for MMF. But the turn is a dimensionless quantity. So generally, ampere is the unit that is used for MMF. For the MMF, generally, same as current. The same unit is used, but as the number of turns increase, the amount of flux produced in the same material is going to increase. That is because of the fact that the current is being encountered by this particular material several times, as many number of times as the number of turns are in the MMF. That is the reason. Okay. Now, if like what we said here in the previous slide, here if I look at the total length of this magnetic field line, which is actually 2 pi r mean. Okay, so let me write this as L. This is the length of the magnetic circuit. Now N is the number of turns and I is the current that is flowing through this number of turns. So we can say Ni by L, Ni by L, which is MMF per unit length of the magnetic circuit. Please remember, this is the unit length of the magnetic circuit and not the unit length of the wire or anything. So we are talking about the length that is along the magnetic path. So this is generally known as H, which is actually called magnetic field intensity. So we call this as magnetic field intensity, which we generally treat this as the cause for the magnetism being established in any kind of material. When a current flows in so many number of turns, it is going to establish a magnetic field, and magnetic field intensity is defined as the root cause, which is MMF per unit length of the magnetic circuit. Okay, so in which case, if I am considering only one conductor that is carrying a current of, let us say, 1 ampere. Okay, and if I am considering a magnetic field line exactly at 1 meter of distance from here. So I'm looking at this from 1 meter of distance. So let us say this particular conductor which is carrying current is O. And let us say I'm looking at the point which is 1 meter away from this particular conductor, and I want to look at what is the kind of flux density we have here. Okay, so at P, the flux density, let us say, is B Weber per meter square. If I try to look at what is the kind of flux density I'm going to have at point P, that is actually B Weber per meter square, and point P is 1 meter away from conductor O. And I'm saying that conductor O, which is carrying 1 ampere of current. This is carrying 1 ampere of current. Okay. So first of all, I should be able to say that if I am looking at what is the path length for this line which is passing through P, I should be able to say that the length of the magnetic path, or magnetic field line along P, that is going to be 2 pi r, and r we said is 1 meter distance, so it is going to be 2 pi meters basically. This is going to be the length of the magnetic path which is flowing along this point P. And 1 ampere of current is flowing through just one conductor, which is actually causing an MMF of 1 ampere turn. That's it, because there is no turn. So I would say MMF in this particular case is number of turns multiplied by the current, There is no number of turn, there is only one conductor, and this is going to have 1 ampere of current. So I'm going to have only 1 ampere turn. If at all, if I write in ampere turn, I have to write it like this. That will be the MMF. So I should be able to say magnetic field intensity, right? That is causing the establishment of or establishing of flux at P will be equal to whatever is the ampere turn, that is MMF divided by the length of the magnetic circuit. So MMF here is 1 ampere turn and length of the magnetic circuit is 2 pi meters. So this is going to be the magnetic field intensity. Very clearly the unit is going to be ampere turns per meter. This is going to be the unit for magnetic field intensity H. And in fact, turns does not have any dimension, so I can simply remove it. It can be ampere per meter, simply. Now, this is causing a flux density of B at point P. So this is the flux density. So if there is a flux density of B at this point, and if I put one more current carrying conductor somewhere at this point, which is going to carry a current of 1 ampere, it will definitely experience a force. It is going to experience a force, right? Because any current carrying conductor that is placed in a magnetic field will experience a force. All of you know that is how motoring action takes place. So the moment you have a current carrying conductor placed at point P, if a conductor, I would say another conductor, it's not even if another conductor carrying one ampere current is placed near or at point B, it will definitely experience a force. It will experience a force which should be actually perpendicular to both B as well as I. So this 1 ampere of current, let me call as some small I. So it will experience a force which is in perpendicular direction, which is perpendicular to B as well as I. That is how it is going to experience a force. So that will be given by the force will be given by B multiplied by I multiplied by L, where L is the length of the conductor. Let me write this L differently because this is not the same as the field line. So let me write this as BIL, where L is the length of the second conductor. So I should be able to say force per unit length if I try to calculate. If I say force experienced by the second conductor for its unit length, per its unit length, will be simply B multiplied by I. And if I is 1 ampere, I should say simply it is B newtons. Okay? But if you had studied the definition of ampere by SI units, if you try to study the definition of SI unit, definition of ampere. So in the definition of ampere, what is defined as ampere is if there are two conductors, each carrying, you can say each carrying certain current say some A ampere, and if they are 1 meter apart from each other, and if they are placed in free space or in vacuum, and if the force between them per unit length is 2 multiplied by 10 power minus 7 newtons, then A will be equal to 1 ampere. So the ampere is defined as that much of current carried by each of the conductors if the two conductors are placed in free space and 1 meter apart from each other, and if they experience a force of 2 multiplied by 10 power minus 7 newtons. This is the definition basically of this particular ampere as the unit of current. This is how SI units define the definition of ampere. Okay, so in which case I should say this B is going to give me basically 2 multiplied by 10 power minus 7 newtons. So I should say in this particular case B is going to be equal to 2 multiplied by 10 power minus 7 newtons. Okay, and H what we calculated, we had written this, H what we calculated was 1 by 2 pi ampere per meter. That's what we calculated. Okay, so we said that this is 1 divided by 2 pi ampere per meter. So in which case I should say if I am giving the root cause which is MMF per unit length as H, the resultant flux density that I am going to establish is B, which is actually 2 multiplied by 10 power minus 7 Weber per meter square. If I am talking about it as B, then it is Weber per meter square. If I am talking about it as the force, then it is newtons. So I should say if H is the magnetic field intensity, which is the root cause for establishing magnetism or magnetic flux in free space. Because I'm talking about the force developed in free space, then the ratio of the flux density to the magnetic field intensity is specified as the permeability of the material. So permeability of the material, what we are going to see here is B divided by H. So I can say the permeability generally is indicated by mu. So mu is going to be B divided by H, and B value here was 2 into 10 power minus 7 divided by H was 1 by 2 pi, and this is going to be 2 multiplied by 2 pi, which is 4 pi multiplied by 10 power minus 7. So this is going to be the permeability of free space. So that is specified as mu naught. So the permeability of any non-magnetic material, generally we are going to call it as mu naught. So this is permeability of air or free space or any non-magnetic material, that is going to be mu naught. So the result, what is because of the result is the established flux. The cause is actually your magnetic field intensity or MMF, and the MMF is going to cause that much amount of flux as much as the material is permissive, or whether it is going to allow. That is essentially going to decide how much is going to be the magnetic flux established. So this mu naught happens to be a material property. Mu is basically a material property. Okay, so mu happens to be a material property, and if I try to write the unit of this mu, I should say it is essentially you have Weber on the top per meter square divided by this is ampere per meter. So you are going to have this as Weber per ampere meter. This is going to be the unit of permeability. So the permeability has the unit as Weber per ampere meter. Both of them are coming in the denominator. So this is going to be the unit of permeability. Okay, so the permeability is basically a material property. So generally what we would say is we will always try to compare the permeability of any material with that of mu naught. So we always write something as relative permeability, which compares the permeability of a magnetic material or something like that. For example, iron. So I should say that mu R is going to be, for example, mu R of iron is going to be the ratio of mu of iron divided by mu naught. So you are going to compare these two and then say this is the relative permeability. So the relative permeability is just a ratio of the permeability of any material to the permeability of air or vacuum or free space in general. So mu R will not have any unit, whereas if you look at either mu or mu naught, they are going to have the unit as Weber per ampere meter. We can also write this Weber per ampere if you try to recall what we talked about inductance. We said L di by dt is also equal to N d phi by dt, which is corresponding to EMF induced in a coil. So I should be able to write this as L equal to N d phi divided by di, where phi is Weber, number of turns N, which does not have any dimension. So I'm going to have Weber per ampere as inductance unit. So which is actually Henry. Weber per ampere is Henry. So I should be able to write unit of permeability as Henry per meter. This is also the unit of permeability. Okay, so I can write generally the unit of permeability as Weber per ampere per meter, or I can write, because Weber per ampere is same as Henry, this will be Henry per meter. Okay, so whenever you're looking at a magnetic field in general, you have to consider definitely the relationship in terms of what is permeability. Unless you have the permeability given for a material, you will not be able to really calculate what is the effect in terms of magnetic flux or flux density for a given MMF or for a given magnetic field intensity. So that is extremely, important. So the permeability becomes extremely important material property whenever we talk about magnetism. Okay. What you talk about as eddy current is electricity, whereas what we are looking at in terms of flux density and so on, that is magnetism. The two are definitely related to each other. So generally, if you look at it, air is a bad conductor of electricity. It's hardly going to carry any current. But air is a bad conductor of magnetism as well, if I may say so. But it is not really behaving like an insulator in that sense. You get my point? It doesn't behave like an insulator completely for magnetic field lines. If it had behaved like an insulator, you would not have had any electrical machine at all. There will not be any existence of any electrical machine. Absolutely. Because especially if you look at motors, right? In a motor, you are always going to have two portions. One is going to be stator, the other one is going to be rotor. The torque developed or the rotation of the rotor is only because of the interaction between the magnetic fluxes or magnetic field created by rotor conductors and stator conductors. If these do not exist, then you are not going to get any rotation at all. That is, the interaction is the one which is creating the torque or rotational power that is actually being created. And between the rotor and stator, you have to have air gap. Otherwise, the rotor cannot rotate independently. If you look at it, generally you are going to have the stator like this, and in the inner periphery, you will have conductors. These are the teeth in the stator structure. So this is going to be the teeth. So inside every slot, you are going to have conductors in all probability. Imagine this entire cylinder is going into the board. So this is the cross section of the cylinder and this is going into the board. So this is the way your stator is going to be. I have not shown rest of the teeth. Of course, everything will have teeth. Teeth has to be there everywhere. And between two teeth, you will have the slot. And inside the slot, the conductors are inserted. This is the way it will be as far as the structure of the machine goes. And you are going to have the rotor which is sitting inside. And the rotor will have its slots actually carved on the outer periphery. Just like how for the stator it is on the inner periphery, for the rotor it will be on the outer periphery. And you are going to have conductors again inserted here between every teeth. Now this will create its own flux and these things will create their own flux. But there will be interaction between these two fluxes only because this is the air gap. Through the air gap also there is some passage of magnetic field lines. Otherwise, there is no way they can interact with each other. So air gap definitely, has some flux lines from the rotor and stator. Both magnetic fields, rotor and stator magnetic fields interact, in fact, in the air gap. They interact in the air gap. So what I'm trying to get at is that although we say literally through air the current carried may be zero unless you create an electric field strength to the tune of 30 kilovolts per centimeter. You have to apply really, really large voltage so that the air gets ionized. Until then, the air is going to be an insulator as far as the electric current is concerned. But for the magnetic field, it doesn't offer a very easy path, but it is not as, completely non-reactive like it is for the electricity. It is going to allow the passage of magnetic field lines It is not as bad as what it offers as resistance for electricity. So that is the reason why generally the electrical machines exist. Otherwise, you will not even see any electrical machine existing. Okay. So having said that, if I try to look at what is the kind of relative permeability we are going to have, for example, for iron. So mu of iron divided by mu naught. So if I talk about relative permeability of iron or steel, generally this will be anywhere between 4,000 to 5,000. It can be as high as that. So what I mean is, if I apply 1 ampere turn of MMF to probably air, if I get only one magnetic field line, but the same 1 ampere turn I apply to an iron piece, then in that case, what I mean is, I just have a conductor like this and I am probably passing 1 ampere of current. And I try to observe what kind of magnetic field lines are produced. How many magnetic field lines are produced? So I may have a magnetic field line going like this and going like this. I try to compare this with another case where I am going to again have a coil like this, but inside that I'm going to insert a piece of iron. So I can show it as though I'm going to have a piece of iron around which I am winding a coil. So I'm going to wind a coil around this. And I'm going to again pass the same 1 ampere of current. Okay. And if I try to observe how many lines are being produced here, it will be almost 4,000 to 5,000 times what I am getting as the magnetic field lines or flux density in the first case. So this is essentially the relative permeability's visualization. You can say it will produce almost 4,000 times the strength of the magnetic flux that it created in air vis-a-vis when I compare it with iron. Okay. On the other hand, if I try to look at something like nickel and iron or nickel and cobalt, if I try to put together, and then this is generally another magnetic material which is going to have very, very high permeability. So in this particular case, if I try to look at mu r for this case, it can be even greater than 10,000. So for some magnetic materials, you can have a very, very high relative permeability. And for air and all the non-magnetic material, you will have the relative permeability to be roughly 1, nothing more than that. Okay. So if I try to look at, let us say I am looking at again the same iron ring which I started with. So I'm going to have the iron ring like this, and I'm going to essentially put a number of turns. So let us say this is the magnetic field line, that is one representative field line I'm taking as the average length of the field line. And I'm going to have the coil wound around like this. So I'm going to have the coil wound around like this. So this is going to go around like this. And I'm going to take out the conductor here, and then whatever is coming here, I'm going to take it out here. So this is going to be some I ampere, and this is going to have n number of turns. Okay. Now let us try to look at it in totality in terms of how we do the magnetic circuit calculation for this. So in this particular case, I'm going to say Ni by L, whatever is the length of this magnetic circuit, that is going to be H. And let us say this is the area that I'm going to have as the cross-sectional area. So I should say whatever is the flux that it creates in this entire ring, that divided by the cross-sectional area, if I just make a cross-section here, that is going to give me flux density. So this is the magnetic field intensity. If I try to calculate for this magnetic circuit system, so this is going to be the magnetic field intensity where L is the length of the magnetic circuit. So this is going to be the length of this red color circular line. And B is going to be the magnetic flux density. So I should be able to say B, right, divided by H I called as mu. But please remember, this is the effect and I'm calling this as the cause because this Ni is MMF and this is the cause and flux is the magnetic effect that is being produced by the current. Okay, so I should be able to write this as Ni divided by L. Okay, and I should be able to say, let's say this is phi divided by A. Okay, so I can say basically B by H is mu, or I can say H by B is 1 by mu. So I'm going to write this as Ni divided by L, and this is phi by A. So I should be able to write this as, this is H is Ni divided by L, and I should be able to write this as B as phi divided by A. So A will go up. So I should be able to write this as Ni by phi equal to, I should write L divided by mu A. I should be able to write it like this, right? So I should be able to write this as Ni by L equal to, Ni by L is this and phi by A. So I had used this essentially to write this as 1 by mu. This is essentially 1 by mu. So I have just taken Ni by phi on one side, L I have taken to the other side. So L divided by mu A. So this is essentially MMF divided by phi is flux. This is going to be called reluctance. So very similar to resistance, we say for certain amount of MMF will establish certain amount of flux depending upon how much is the reluctance offered by that particular material. Okay, so this L by mu A we call as reluctance, which is very similar to when we write for the resistance rho L by A. That is the resistance. We write this as resistance, where rho is the resistivity of the material. The same way we would say mu is the permeability of the material. Okay, so we can say that we would be able to calculate the exact value of flux provided I know the MMF and I know the reluctance of the material. Okay, so we'll continue with magnetic circuit calculations. I have only introduced the basic concept behind magnetic circuits, nothing more than that. So we will look at more of magnetic circuit calculation as we go along. So in tomorrow's class, I will introduce the concept of magnetic circuit calculations and then we'll go further along the same lines so that we understand the electrical machines better.